Hello and welcome all to today's session. Today we will be discussing certain numericals on the ultrasound. So, let us get started. So, before starting with the numericals, I would like to discuss certain aspects or a few points about what is ultrasound. So, as the name suggests, there are two parts, ultra and sound. And first, if we define sound, they are basically longitudinal waves that travel through various media. The the point to be noted here is a medium is required. Okay, that's now this media can be either a solid, a liquid, or a gas. And in the absence of media, these sound waves cannot travel. And another thing to notice or make a point of that these are longitudinal waves. That means the vibration of the particles are in the direction of propagation. There are other kind of waves as well. For example, we have transverse waves where the direction of propagation is perpendicular to the motion of particles is perpendicular to the direction of propagation. Now once we understand what is sound, basically waves that travel through a media, what is ultrasound? So, we humans can perceive sound in a specific range. To be precise, an average human can hear any sound between 20 hertz to 20 kilohertz. Now, anything which is above 20 kilohertz, we call it as ultrasound. Now, like any waves, even ultrasound has certain characteristics such as frequency, wavelength, and speed. Okay. So, frequency is number of cycles per unit time. For example, if this is the time and this is the propagation of the wave and this is the time. Let's suppose in a given unit of time how many cycles we have. Now, this will give you the frequency, and if you have any two specific identical points, basically let us say we have peaks, and the distance between any of these two peaks would give you the wavelength. Okay. So, then we let us talk about the propagation. Okay. Depending upon the medium, the sound waves propagate differently. For example, in air sound has a different speed. In any other media such as water or a solid like such as wood, iron, sound waves have a different speed. And then there is something called as reflection. So, when you say reflection, the first thing that comes to your mind might be a reflection of light by a mirror. Similarly, we can also have reflective surfaces for sound, or to be precise in this case ultrasound. So, if we have any two if we have a boundary which separates two different medium, then there will be some reflection of these ultrasounds. Today we will be diving a little deeper into how this reflection takes place based upon some numericals. Then at the end, the idea behind learning about this ultrasound is finally to use it in some application. And when we talk about ultrasound, okay, the first thing that comes to our mind is imaging, medical imaging. So, basically ultrasound, or as we also call it in layman terms as a sonogram or sonography. If you visit any hospital, there might be certain boards, certain signs which will direct you to a sonography room or an X-ray room, and there you might see some certain terms such as doppler, 3D doppler, sonogram, etc. So, basically it is a diagnostic technique, and most importantly it is a non-invasive and a painless technique which makes use of ultrasound traveling through your body to image the internal organs. Okay. So, what happens is whenever the suppose this is your body or a part of your body, and inside there is an organ. Okay. So, what would happen is some ultrasound will be directed towards your body, and there is this boundary where some of the some ultrasound would go inside your body, strike your organ and get reflected. Now this is the incident wave and this is the output signal. Okay. Now using this output signal you can form some images which would give you an idea of what is the condition of your organ. So if you see this figure, this is one example of an ultrasound you might have seen. This is just a stock image of what do you say, a schematic of how an ultrasound acquisition looks like. And here we have a transducer which we usually use to get an ultrasound, to do an ultrasound and get an image. Okay. So now if there is something called as, if you have been through an ultrasound, you would see that the technician takes a transducer and puts some gel on it and then performs the process on your specified body part. Now what this gel does is it reduces the acoustic impedance, or it matches the impedance between the transducer and your body, and today we will be looking into that. So the first numerical here we have, the problem says to calculate the distance of the object if an acoustic burst is sent in the air and received after 1.5 seconds. So that is the first part of the problem. Now like I said, sound waves require a medium to propagate, and here this medium is air. Okay. And it is given that the speed of sound in air is 340 meters per second. Okay. And it is told that the acoustic burst which is sent is received after 1.5 seconds. Okay. So here this 1.5 seconds becomes the propagation delay. Okay. I am sorry. .5 second is the propagation delay, and what we since the medium is air, the speed of sound, let us say V, is 340 meters per second. Okay. Now what actually is happening in this case is, there is let us say a device, let us say a transducer, which is giving some acoustic signal. It comes and hit the object and gets reflected back. Now this whole time in going for the sound that sound is taking to go to the object and return back, this is your propagation delay or the time of propagation. Okay. And which is a sum of the time it takes to go to the object and time it takes to come back. Now since the medium is same, okay, since the medium is same, for the same distance the time taken to go to the object and come back would be same. So let us say it is 2 times t1. Now the total propagation of time is 1.5 seconds, therefore t1 becomes 1.5 divided by 2, that is 0.75 seconds. Okay. And it is a very basic formula that the distance is equal to speed into time. Now since we know the speed, that is 340 meters per second, and we know the time, that is 0.75 seconds, the answer comes out to be 255 meters. So the first part is distance is equal to 255 meters. Now the second part of the problem says that what would be the propagation delay if the medium was water and the distance was same. So here using the same formula we will rewrite it as what we need to calculate is t, okay, the time in this case, which would become distance upon the speed, and this is speed in water. Okay, here the speed was in air, that was 340 meters per second, and now here we have that the speed of sound in water is 1480 meters per second. Okay, so let's solve this. The distance is same as 255 and the speed is 1480, which gives us 0.172 seconds. Okay, now you might make a mistake here that this actual 0.172 second is the actual propagation delay or the time of propagation, but that is not the case because this distance is 255 meters. So, right now what you have is only the time it takes from for the sound to travel from the transducer to the object, that is half of the propagation delay. So, the actual answer, the actual propagation delay in water would be 2 times 0.172 second, which comes out to be 0.344 seconds. That is the second part of your answer. Okay. So, now let's move to the another problem, that's a numerical number 2, and it's quite interesting because here we introduce another concept which we will see. So, the problem here says that the transmitted acoustic signal, the frequency is given as 2.5 megahertz, and it is given that the beat frequency that you receive is 650 hertz. Now, we are told to calculate the blood flow velocity. Okay. So, before that let's see the diagram, the figure that we have. Here we see in a transducer there is a transmitter. Okay. So, sound waves are traveling at this is 2.5 megahertz. Okay. And from the blood particles this sound is reflected. Okay. And there will be some frequency. Okay. Now, we will see what this exact thing is. So, what is happening that ultrasound is transmitted at 2.5 megahertz. Now, it is ultrasound, we know it because the limit of hearing for humans is 20 kilohertz, and 2.5 megahertz is fairly larger or higher than 20 kilohertz. So, now we know that this is ultrasound. It is it travels and gets reflected by the blood, and it is received by the receiver. Okay. So, okay. So, let us see the concept which we will be using right now in this case is Doppler effect. Okay. How it is defined is there is a shift in the observed frequency of sound due to motion of either the observer or the surface or the source. Okay. So, in this case let us divide this problem into two parts. So, the first case would be where it is transmitted. Okay. The frequency is transmitted at 2.5 megahertz, and some frequency will be received or seen by the blood. Okay. In that case what would happen? So, let me write here, this is the source in this case. Okay. And here blood, this is the observer. Okay. And this is the source. So, what is happening here? Blood is flowing, let us say the blood is in this case moving away from the transducer. Okay. This is the motion direction of motion for the blood, and here we have the source, and we have some velocity of sound here. Okay. So, let us assume that the velocity of sound is here 1480 meters per second, which is same as the velocity of sound in water. Let us assume this is the case here. Okay. Now, what would happen here is we have velocity of the observer. Okay. In this case that is blood, and this we need to calculate, we do not know this. Okay. And then we have the velocity of source. Now, source is your transducer which is stationary, it is not moving. So, this becomes 0. So, in this case what we would have is the frequency observed by the blood is equal to, this is 2.5 megahertz. Okay. So, and what we have here, okay, let us not put the values right now. Okay. So, we have here for the source, frequency of the source, and we have, since this is moving away, okay, since the blood is moving away, here we will use a minus sign. Okay. And let us say this is velocity of blood, and here we have velocity of the source. Okay. So, here since velocity of the source is 0, we are not putting it here, and the velocity of sound, here we have Vw, and this is the velocity of blood. So, this becomes your first case. Now, going back, we will see the second case. Okay. So, in the second case, the sound is reflected back from the blood. So, now this becomes the new observer, receiver becomes the new observer, and blood becomes the new source. Okay. So, let us see what happens in this case. Okay. Let me clear this out, the first case. Okay. So, here in this case what is happening, that your observer, which is the receiver, is stationary. Okay. So, this becomes 0, and this source, which is your blood, it is moving away. Okay. So, here in this case we will use a plus sign. So, in the second case what is happening is, for the source we have this becomes your second equation. So, in the first case what we had was the frequency of the observer, but here the observer was blood. So, we will replace this thing, okay, the suffix, it becomes, okay, and here in this case as well the observer, the source here in the second case is blood. Okay. Now, if you see these two equations carefully, we can replace the F blood, that is the frequency of sound from when blood is the source, by equation 1. Now, replacing this, what we get is F observed becomes Fs, that is the source, to okay. So, this becomes your new equation, and by after some mathematical operations we can see that these two cut out, and the F observed upon Fs is basically this term. Now, further operations, after further mathematical operation would give you okay. So, this is your final equation. Now, it is in the problem it was said that the beat frequency, okay, was 650 hertz. Now, what is beat frequency is something we measure, that is the difference or a difference between the two frequencies that you are having. So, in this case what is what we have is, one is the source frequency, which was 2.5 megahertz, and another was the observed frequency. Okay. So, the difference between the frequency that is transmitted and the frequency that is received, that would be your beat frequency, and in this case that we have it here as 650 hertz. Okay. So, in this case what would happen is your f observed minus f s is 650 hertz, but in this case what might happen is that the f observed might be lower than f s. Okay. And beat frequency we cannot have a negative value, because when it is measured it is just a magnitude. So, we will put this mod sign. Okay. So, if you see your final equation that we have boxed in, the on the RHS we have a negative value. Okay. So, let us not have a negative value here, we'll make it positive. So, we have Fs minus F observed upon Fs plus F observed is equal to Vb upon Vw. So, what you want to calculate here is Vb. Okay. And we know this is the beat frequency. Okay. The beat frequency we know here, that is 650. So, here we can say that your f s minus f observed is 650. So, your f observed becomes 2.5 megahertz, that is, okay, let me, it would be actually we will write it again here. Yeah. So, your f observed finally becomes Fs minus 650, and Fs is what? 2.5 megahertz. So, what we have here is 2499350 hertz, and in the question in the problem it was told that we can assume that this the significant digits are up to 7 digits. So, here we have f observed. Now, if you put substitute this value in this equation, we would have into 650 upon, now adding Fs plus F observed would give you 4999350, and the value that you get here is 0.192 meters per second. So, this is your final answer. The velocity of blood that you are imaging is 0.192 meters per second. Okay. Okay. Now, let us move to numerical number 3. See, here it says that calculate the ratio of intensities reflected back to the transducer using the tables for calculation. So, here in this case what happens, suppose here was the transducer, you will have some incident beam. Okay. Now, here what would happen, some of it would get reflected definitely. Okay. We are not considering that. Now, let us assume that here what you have here, this the source that you have here is basically some of the sound waves are getting transmitted. Okay. Now, from this transmitted wave, some would go to the bone, towards the bone and tissue interface, and some would go to the tissue and muscle interface. Okay. Now, let us erase this part. Okay. Yeah. So, let us say this is the incident intensity, that is I1. Okay. Now, what would happen here is, now again some of it would get transmitted, okay, and some of it would get reflected. So, let us call this reflected part from the bone as I2, and the transmitted part to be I2 dash. This also would be same intensity I1. Okay. And let us say from tissue and muscle interface also there will be some reflection, let us call it I3, and the reflected back the reflected part would be let us say I3 dash. Okay. Okay, it might not be visible, I will just write here I3 dash. Okay. So, what we want to know is the ratio of intensities reflected by back. Okay. Since the transducer is here, okay, transducer would be here, and there will be some matching layers. So, there will be some gel which will reduce the reduce the acoustic impedance. So, whatever sound waves are being incident, we can assume that it is being incident from this surface, and also whatever is reflected back is also at this surface, at this boundary. Okay. So, let us say this is I1 which is incident on these two interfaces, interface A and interface B, and what is reflected back is I2 and I3 that we need to calculate, okay, or rather the ratio that we need to calculate. So, to solve this problem, what we need to know is a concept called as acoustic impedance. So, what does it actually mean is basically it governs the reflection of sound at the boundaries of two different surfaces. Now, we saw there is a boundary of soft tissue and bone, then there is a boundary of soft tissue and muscles. So, in this case we would we should know, we need to know what is acoustic impedance. So, basically it is denoted by Z, okay, it is denoted by Z, and the formula says Z is equal to rho into V, where V is the speed of sound in the given media and rho is the density of the media. Okay. So, in the previous table we already have let us see, we already are given the density as well as the speed of sound in that particular media. So, what we can do is we can calculate the acoustic impedance. Okay. Now, another thing that we need to know before approaching this problem is intensity coefficient, reflection coefficient, or the coefficient of reflection. So, this is the formula that gives you the ratio of the intensity. So, the definition is the ratio of intensity of the reflected wave to the incident of intensity of the incident wave. So, let us suppose this is the boundary, okay, and the incident beam was I1 and the incident wave was I1 and the reflected back is I2. So, this ratio of intensity would be given by I2 upon I1, and this is your coefficient of reflection. Now, the formula for calculating this coefficient of reflection is Z2 minus Z1 upon Z2 plus Z1 the whole square. Now, what are Z1? What is Z1 and Z2? Basically, Z1 is the acoustic impedance of the first media and Z2 is the acoustic impedance of the second media. Okay. Now, if we know this part, okay, we can start approaching the problem. Great. So, since we know what is the density and speed of sound, we can use this formula Z is equal to rho V and start calculating the acoustic impedance of the soft tissue. For soft tissue, it would be we have these two values, we would just start multiplying. So, basically it gives us 1.341 into 10 to the power 6. Okay. Okay, let us not worry about the units right now, but it is calculated in trials. And for the muscle we have 1075 into 1590, which would give Z2 as 1.71 into, or let us say we keep the significant digits the same, and similarly for the bone also we have 6. Okay. Now, since we have these values, we would start calculating the coefficient of reflection, intensity coefficient, intensity reflection coefficient. Okay. So, for the first interface that we have the tissue and bone interface, let us say it is AA. Okay. So, what would happen here is we have Z2 and Z1, that is 1.709 into 10 to the power 6 and 1.341. So, the Z2 minus Z1 upon Z2 plus Z1, the whole square would be something like 1.709 minus 1.341 upon whole square. Now, if we calculate this, the answer comes out to be 0.0146. Okay. And similarly, if we calculate for the tissue and muscle interface, we have something. Oh, sorry, my bad. This was actually for the AA was for the tissue and muscle interface, and now we will be calculating for the tissue and bone interface. Okay. So, here it comes out to be 0.4345. Okay. So, here what is happening is we have these two values. Okay. Let us make a note of it. So, let us say the intensity I1 was 100%. Okay. So, let us talk about the tissue and muscle interface first. Okay. So, in this case what would happen, your I3 upon I1, that is the reflected wave, the intensity of the reflected wave and the divided by the incident wave intensity would be AA, that is 0.0146. Okay. So, now this was your E1. Okay. And similarly, we have your I2 upon I1. Okay. This was AA, and your I2 upon I1, that is between the bone and the tissue, we are getting something as 0.4345. Okay. That is your AB. Now, we are told that we need to calculate the ratio of intensities reflected back to the transducer. That is I2 upon we need to calculate I2 upon I3. So, if we take the ratio from the above two values, we get something like 0.4345 upon 0.0146. And it comes out to be 29.76. So, your final answer is 29.76. Okay. That is the ratio of the intensity that is reflected back to the transducer, that is I2 and I3. Okay. So, that is pretty much everything we had to discuss today, and I am hoping that by these three numericals we learned something new. The first numerical we understood how can we calculate the distance, okay, by knowing the time of propagation or the propagation delay of the ultrasound. In the second numerical, we learned something about the Doppler effect and how we can calculate what is the what is the basically motion, what is the or the speed of the object we are trying to image as in that case. And in the third one we knew what the importance of the acoustic impedance and how it plays an important role in the quality of image. If there is a very good what do you say impedance matching, that means the acoustic impedance is very low. Most of the sound waves or ultrasound waves would straight away transmit with minimum losses. But if the acoustic impedance is very high, okay, if the acoustic impedance is very high at the surface itself, then what if let's suppose 100% of the is the incident intensity, okay, and if the acoustic impedance is very high, it is possible that only 1% of your waves would actually enter the body or the subject you are trying to imagine, subject you are trying to image. And using only that 1% of the residual intensity, we would be getting the image. Okay, so thank you. That's all for today.